Okay, here's a quick MATLAB implementation of gradient descent. The function that we are trying to minimize is this really simple function, 3x1 square plus 4x2 square. We know that the minimum of this function is going to be at x1 equal to x2 equal to 0 because this is like the sum of squares essentially, and the minimum value it can take is going to be 0 because it's at least 0 because for any other value of x it's going to be part. So we know everything about this function, but let's see how gradient descent works in finding the minimum of this function. Okay, so let me just walk through it. It's just implementing the formula really of gradient descent. The number of unknowns is 2, x1 and x2. We want to find the values of x1 and x2 that minimizes this function. Um, let's have an initial seed. We're just going to use rand n to generate initial seed. 2 comma 1 initial seed. So if you go rand n 2 comma 1 unknowns, it'll generate a normally distributed random numbers. Okay, so let me just this run this. So some initial seed x initial is that some huge 17 and then 1. We're going to take 1,000 steps, let's say, and alpha, the learning rate, we just chose arbitrarily to 0.01. These two things we will come back to. F accuracy is how accurately can we evaluate the function itself. Um, and I'll talk about the rationale for this maybe in a later video. Okay, so we're going to store um, the successive iterates of x in this um, cell array called x iterates, and I'm using curly braces and setting the first iterate to 1 x initial. uh, F value initial, we can just evaluate the objective function. So this is actually a way of evaluating any function. Now I could have just said f objective function of x iterates. Here I'm just using f eval. Um, of course, I need not have used it, but if I quickly sort of wanted to change, um, f eval is most useful if you want to call a function, but you do not know what function you want to call a priori, right? Before, like for instance, if you wanted a function, if you wanted to write a function where that function is calling some other function, and the other function that you want to call is actually an input to the original function in some sense, then you might want to use feval. Okay, um, it's not super important in this context. Um, okay, so this is just plotting stuff. We're just plotting the initial guess, initial function value, etc. And this loop is really the gradient descent. Um, this gradient threshold, which is set to 1 in 10,000, is basically checking if the gradient is really small so that we can the stop the gradient descent. Okay. Um, so we say for I equal to 1 to number of steps, we just display some step number. Here we are actually finding the gradient of the objective function at the current iterate. And it uses the accuracy with which the objective function can be evaluated. It uses what's called a central difference formula. Basically, what is a gradient? It's just derivatives. You can find the derivative by doing divided differences, namely evaluating the function at two neighboring points, taking the difference and dividing by the difference, and basically the parameter the values at which the function has been evaluated, right? So we'll talk about that in a separate video, but it's basically using a central difference formula to approximate the gradient. So basically, it's saying things like df by dx1 is basically f um, at let's say x1 minus f x1 plus h or something like that, x1 minus h divided by 2h. Okay, so this is basically the central difference formula, where you take a step in one direction, take a step in the other direction, divide by uh, the total distance by which you steps, which is 2h. That gives you the derivative df by dx1. Okay, so that's, and then you do the same thing for x2. That's basically central difference formula. And then here is the key step. It says exit rate psi step plus 1 equals exit rate psi step plus alpha, the learning rate, times negative of the gradient, which was computed here. Okay, this is gradient descent, that simple step. Previous step is just computing the gradient. Oops, computing the gradient. Here we evaluate the function at the new point just to keep track of how the function changes. We do a couple of plots. We can plot where the iterates are. We can plot how the function value is changing. And then here we say if normal to gradient is less than some small threshold, we stop the gradient descent. This talk and this tick allows us to display the elapsed time between these two, this loop. And really that's it. These two um, cells are trying to do the same optimization problem but using fmin-nunc or fmin search. You can see how they work, but let's just run gradient descent first. So those are the initial points, initial values. Now I'm going to run the gradient descent loop, and you will see the function value decrease, hopefully. So you can see the function value decrease. It's slow because it's plotting. So it's gotten pretty close to 0. And here, I guess it's getting close to 0, but not maybe close enough. So if you comment out the plotting, this will go much, much faster. Should probably just fast forward this um, part of the video here. We see we are doing step number blah blah blah. Okay, so you get the idea. I'm actually going to Control C out so that we can speed this up dramatically. Okay. Um, so I'm just going to comment this out and run this all over again. It ran really fast, like within a blink of an eye, 0.029 seconds. All that plotting was slowing things down dramatically. The whole thing ran in um, I don't know, 1/50th of a second, roughly, or 1/30th of a second. In any case, very fast. And x result of gradient descent is it's pretty close to zero. It's not maybe as close to zero as you might like. If you wanted even closer to zero, we might decrease the gradient threshold here. Took a few more steps, um, and we got an even lower x result, closer to zero. Anyway, so it's done a pretty good job. It's gotten the function value really close to zero. The function value is now going to be 10 to the minus 10, because if x's are 10 to the minus 5, x squared is going to be 10 to the minus 10, right? So it's very small. Okay, so how well does fmin-nunc do? Let's run that. So we can, by the way, check how many steps gradient descent took. It took about 259 steps. Each step, actually, it's computing the gradient. At least the way we computed gradient, it's using two function evaluations. So it called the function about 500 times to get this level of accuracy. Now let's look at fmin-nunc. With about 21 function evaluations, it turns out fmin-nunc got the function value to 10 to the minus 12, which is really good, really fast, right? It's a much more sophisticated sort of method, fmin-nunc is. Um, and then fmin-search, let's see. It looks like it took 99 function evaluations, perhaps, to get, again, 10 to the minus 9-ish. Pretty good. So lots of methods. Um, we will use fmin-nunc, for instance, as we did for logistic regression. But for eventually, when we do, it turns out, much more complex optimization problems involving neural networks, it turns out that the standard method to use is gradient descent and some modifications of it for specific technical reasons that perhaps we will get into in a later lecture. Okay, it turns out that for a class of nonlinear problems, um, maybe a few hundred, few thousand unknowns, fmin-nunc and things like that are pretty good. This is fmin-search, I guess. But for the very large scale optimization problems that arise uh, with neural network or deep learning, it turns out that gradient descent actually beats these other methods, or these other methods are just barely feasible, if at all, because they rely on much more information. So gradient descent, even though it's very simple and maybe for small problems it's not the most efficient, it turns out it's really good for really large problems that arise in machine learning. So we'll do that.